Good morning and good evening, everyone. I'm Jinghu Zhang, a researcher from Recon EIP. Today, I'm going to host the TrustML Young Study Seminar. Before that, allow me to briefly introduce Recon EIP to our valuable guests, Mikhail and Tianyu. The full name of Recon EIP is the Recon Center for Advanced AI Project. It is founded in 2016 at the Research Center for the Max EIP project. EIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. EIP aims to enhance AI fundamental technology and its real-world applications. We encourage the collaboration with various researchers and engineers in related fields. We will be very grateful if guests and our audience can visit us in our Nihonbashi office in Tokyo in the near future. Then today, let's firstly introduce Mikhail, then I will introduce Tianyu when his talk comes. Mikhail Yurskin is a research staff, a member at IBM Research and MIT IBM Watson AI Lab in Cambridge, Massachusetts. His research interests are model fusion and federated learning, algorithmic fairness, application of optimal transporting machine learning, Bayesian modeling, and inference. Before joining IBM, he completed PhD in statistics at University of Michigan, where he worked with a long wing. Hi, Mikhail.
Hello.
You could get started your talk. We sincerely welcome you.
Okay, great. Okay, and thank you for the introduction. And thanks everyone for joining my talk today on practical individual fairness. So to begin with, let's look at a simple case study. So suppose we want to do a sentiment classification task. So that's a very simple natural language processing task. So we want to classify words as positive or negative. So the positive words are, for example, admire, adorable, joy, and negative words such as aggressive and distrust, nasty. So it's a pretty standard task. And so we can use a deep learning and word embeddings to get 95% test accuracy without really trying so hard. So the question is, have we solved the problem? And of course, we got a good accuracy, but what if we deploy such a system in practice? So what if we try to use it to evaluate the sentiments of, let's say, movie reviews, restaurant reviews, and so on? Like the different texts encountered in the wild might contain human names. And the question is, what is the sentiment of a name? What will our system do? So ideally, we would like it to kind of, the name to not really affect the sentiment of a sentence because it should be neutral. And here we would like to test whether it is the case. So for that, we take the names that are more popular among the European American population, such, for example, Adam and Ryan, and the names more popular among the African American population, such as Alonso and Terry. So we look at the average sentiment score for each of the groups of names, and we see that our system that was actually quite accurate in predicting those adjectives that we wanted them to predict, it assigns very different sentiment scores to different groups of names. So in particular, the Caucasian names are on average a lot higher, receive a lot higher sentiment. So one way to deal with it is to use what is called a group fairness. So the main idea of group fairness is to essentially say that on average, the outcome for different protected groups, such as, for example, based on race, should be the same. So now we've aligned those averages. So group fairness is satisfied, but is the system really fair? Well, from the perspective of Tyree, it doesn't really appear very fair because the name Tyree still is receiving a very low sentiment score. So this is a violation of individual fairness, which asks us for all similar individuals to be treated similarly. So in this case, we can use our techniques to achieve basically the same sentiment scores for all the names. So in this case, not only the average are basically the same, but also just all the names are generally comparable in their predictions. So all this is a very little cost to accuracy. So in this case, the original accuracy was 95%, and using our method, the accuracy is 94%. So here we show that achieving individual fairness is possible without really sacrificing accuracy. And it's also an example of a situation where the other popular notion of fairness, group fairness, is not quite enough for us. So let us discuss some more modern individual fairness problems. So for example, occupation prediction from a person's biography. So it's a more serious natural language processing task. So we are kind of taking as an input a person's biography, summary of their work experiences and so on. And we try to predict their occupation. So such kind of systems could be used by recruiters to, let's say, identify a promising talent from, from so many candidates online and so on. So here we are looking at the simplified biographies represented by a sentence. So for example, he graduated from law school with honors, and the prediction for this biography that this person should be an attorney, which is reasonable. But if you change a single word, we change a gender pronoun from he to she. So she graduated from law school with honors is suddenly predicted as a paralegal. So again, these two inputs are comparable. So it means to satisfy individual fairness, the predictions also should be comparable. However, they are not. So it is an example of an individual fairness violation. Another example that is also like a kind of application that is important today is a toxic comments classification. So the systems, such systems are used to moderate online discussions to make sure that every voice is heard, that the discussions are inclusive and safe for everyone. So here we are considering two sentences. So the first one is my best friend is straight. So it doesn't seem like a toxic one. So the prediction is non-toxic, which is good. But if you just change this identity word straight to gay, the prediction suddenly changes to toxic. So this is again a violation of individual fairness. So such problems arise, for instance, if in the training data, the word gay was oftentimes used in the sentences that are labeled as toxic. So the model learns to associate the word gay as being toxic. And there are many other identities that are oftentimes discussed in the online conversations in a negative context. So that leads to them being sort of predictors of toxicity without a good reason for that. So we will come back to this problems later in the talk, but I wanted to kind of motivate the idea of individual fairness and also to demonstrate what kind of individual fairness problems we want to solve today, because the sentiment classification one maybe was a simplified example, but it's nonetheless like a good demonstration. So maybe perhaps one question that people in the audience might have: what if we just remove the names? So this solution is called blindness in the fairness community. So just trying to remove names as a pre-processing step, trying to remove gender pronouns from biographies, things like that, right? So unfortunately, oftentimes the bias could be somewhere else where we didn't expect. So for example, in our sentiment classification experiment, so the system that we trained to predict the sentiment, now we try to pass two simple sentences: let's go get Italian food and let's go get Mexican food through that system. And we again see that the sentence that has Italian food in it receives a higher sentiment. So, I mean, again, we can try to also remove those, Italian and Mexican, but it's kind of hard to think of all these problems in advance. Let's say with the biography classification, one common problem is if we, let's say the information about gender could be also correlated with the hobbies of a person, and some other things, maybe a particular school they went to could be like, like predominantly like single race or single gender. So because of that, just simply removing the this type of information is not enough. And also interestingly, in this example, when we tried our individually fair model on it, so we actually got approximately the same sentiment for the two sentences. So really, we didn't consider that during the training at all. So we're kind of focusing on being individually fair with respect to names, but turns out that kind of the identifying bias in the word embedding space for names also relates to bias in other parts of it too. So another interesting example that again demonstrates that blindness is not a good solution is this case from a couple of years ago with an Apple card. So this card is a credit card that was created by Apple together with Goldman Sachs. And shortly after, many people, so for example, some entrepreneurs, so they went on Twitter and started complaining that the credit card is being sexist. And typically the complaint would be of the form that the person who complained had a spouse, which was a homemaker, and that the people would file the tax returns together and so on. So they kind of share all the assets and they should have the same credit score, yet the credit score algorithm would assign a lot lower credit score to the homemaker spouses. So this is interesting because this happened in the sphere of banking in kind of, like a real situation. And what's important to note about banking is that in the United States, there is something called Equal Credit Opportunity Act that's been in force since late 20th century. And essentially it says that the average outcome for for any group should be comparable or within 4/5 of the average outcome for the majority group. So in a sense, it's again a group fairness requirement that is, written in the law, and very likely that this law is being complied with. But also another aspect of it is that actually the gender is not allowed to be used in those algorithms. So those are all requirements, but yet we see that the fairness are violated, and here it's kind of with respect to a subgroup of women. So again, we see that the blindness is not quite a solution, and also group fairness can fail in some cases. So to address all these problems, we developed an individual fairness pipeline. So essentially a series of methods and algorithms that together allow us to achieve individual fairness in practice. So the pipeline consists of learning the parametrics from data. So that's an important component of individual fairness. So that basically tells us which individuals are comparable and which are not. Oftentimes, so the starting point for kind of trying to introduce fairness into machine learning systems is not just the data, but it's oftentimes already an existing solution. So oftentimes companies would have pre-trained systems that they're already using, and they want to fix some biases in those systems. So that's why the first step, instead of just training a model, actually the first step is to audit an existing model that's currently being used for violations of individual fairness. And if such violations are found, the quickest solution possible and the easiest is to post-process the trained model. So post-processing means we don't actually need to retrain the model. We don't even need the access to model parameters. All we need to do is just to have the predictions of the model, and then we can do some kind of manipulations with them to improve the fairness of the model, just acting in the space of the outputs. And finally, of course, the ideal solution, the eventual solution that we want to strive for, is you want to train an individually fair model and replace the existing model with the one trained with individual fairness in mind. And we also study the extensions to beyond supervised learning and kind of beyond like usual models of ranking and boosting. So I wouldn't cover them in this talk, but please take a look at the references that I would share to learn more about that. Okay, so the first we will actually start with auditing. So I will explain what is the key quantity that we use to understand whether individual fairness is satisfied or not. So here we introduce this notion of distributional individual fairness. So the key idea of distributional individual fairness is to find the map T. So we have a machine learning model H that we are trying to audit. So we're trying to find the map T, which we call an auditor, that basically finds fairness violations. So what it does, it tries to modify the inputs X in such a way that the difference in outputs is maximized. Meanwhile, the difference in input with respect to the fair metric, and we'll get to the fair metric in a second, is small. So basically it says, find me comparable similar individuals such that the difference in outputs is big. And so if this auditor manages to find such comparable individuals, so then the DIF will be large and essentially demonstrates the violations of individual fairness. So again, going back to our earlier examples, so for example, consider like an input sentence X to be here graduated from law school with honors, and the machine learning predicts a turn. So what the auditor will try to do, it will try to kind of find a comparable sentence. So for example, she graduated from law school with honors should be comparable and should be small in the fair metric in comparison to the he counterpart. At the same time, the difference in the outputs is big because it's a different prediction. So this basically is how the auditor operates in this example. So the similar goes for the toxic common classification. So the auditor should find a kind of my best friend is straight would be the original input, and the auditor should find my best friend is gay as another input that highlights the violations of individual fairness. I also wanted to kind of make a connection to some studies that was done by two economists in 2004. So this study is not a machine learning study. It's kind of more of a study of like a social science kind of study. So where they investigated the racial bias in the US labor market. So what they've done in 2004 is that, well, they responded to the job ads in Boston and Chicago newspapers to use fiction as resumes. So they randomly assigned African Americans of white sounding names to the resumes. So basically they perform the audit. So let's say the original resume is the one with the white sounding names, and they create an exact copy, but just change the name to an African American sounding name. So this is what the T of X auditor would do in the DIF definition. So after that, they collected the results. And so they concluded that there is a discrimination against African Americans. So the resumes assigned white names received 50% more callbacks for interviews. So this basically indicates that the value of the DIF is large. And so kind of here, the DIF essentially is a mathematical formalization of the study of the US labor market from 2004. Okay, so now, of course, an important part of it is how do we get a fair metric? So intuitively, when we look at these sentences, such as, he graduated from law school, she graduated from law school, yes, they do look comparable to us, but we need an actual mathematical quantity that would, take two inputs and then produce a number. So how do we get that? Well, so we developed several techniques for learning fair metrics from data. So, and currently we have these three different methods that, each of them has a use case depending on the type of data that we can get. So one example is pairs of comparable and incomparable samples. So a human kind of ideally should label some input sentence as comparable and incomparable for us to perform the learning of the fair metric. Then another method is using protected attributes, so which is oftentimes kind of the available data for the group fairness algorithm. So here we can use it also to learn the individual fairness metric. And the last method is using groups or a single group of comparable samples. So in the end of the day, we always learn a fair metric of this form of a generalized Mahalanobis distance. And so let's take a look at some examples. So actually today we will already in this talk, we've applied one of these methods. So we used a group of comparable samples in our sentiment classification task. So there we learned the fair metric using the war embeddings of popular baby names. So we didn't use the names that that we were using for evaluating the fairness. We just downloaded like an arbitrary list of popular baby names and then used our method that we call face. So the key idea is very, very simple. So we just take this group of comparable samples and we find directions of major variation using a principal component analysis as an example. So now that we found them, we ignore them in the fair metric computation. So intuitively, if the group of samples is comparable, then all the variations in them, is not kind of is unfair in a sense, right? So it's unfairness in the embedding space. So when we compare such two inputs, we want to ignore that type of variation. So that's exactly what we do in this method. So again, we obtain sigma, we obtain the fair metric, and that's what we used in the example with the sentiment classification. That's what we'll actually, or like a version of this, we will use for occupation prediction and toxicity classification. So another example is where we use pairs of comparable and incomparable samples. So this method we call explore. So here we also, the idea is quite simple. So if we feed a model to find sigma, to essentially make sure that whenever the fair distance, the dx, is small, then we kind of build a prediction model to predict whether a sample is comparable or not. So it's essentially a variation of like a logistic regression where the inputs are triplets instead of pairs. So we have like a label, comparable or not, and we have x1 and x2. So it's also a fairly simple model to use, and we found some interesting applications for it as well. Okay, so now that we've talked about the fair metric and the auditing, so our next step before we kind of do the training, we actually want to post-process an existing model. So this is interestingly working at IBM. So I also participate with some interactions with clients. So that turns out is a very popular method because, again, as I mentioned, many businesses already have some models that they're using, and it's a lot easier and more desirable for them to just post-process them, so they don't need to really change their model. Because oftentimes the models that are used by companies, there is a lot of steps in them, a lot of time has been spent to tune them and so on. So it's not so easy to convince someone to commit to just discarding the models that they're using for their business. But post-processing is something that people are oftentimes willing to consider. So for post-processing, for individual fairness, they use this kind of a graph analogy. So what we do is we represent all our data on a graph. So remember here, all we have is the predictions of the model. We also need to measure the fair distance between the different inputs. So this can be done absolutely separately from the model. So for example, we just take like a pre-trained bird to embed the textual inputs, and then we learn the fair metric in the space of bird embeddings, or it also can be done for tabular data and so on. So once we measure this fair distance, so we can build a graph where there is an edge between two data points if their fair distance is small. So here we have these applicants for software engineering jobs. So we have, for example, Alice and Charlie. They have the same qualifications. They both know Python and C++. So that's why there is a big edge, kind of a fat edge between them. So meaning that they're very similar from the perspective of fair metric. So is Dave and Alice, and Dave and Charlie are also similar. So even Bob, they have different qualifications. So that's why they're not similar to the others. So the axis and ticks here represent the model output. So the model essentially rejects Eve, Alice, and Bob, and the model accepts Dave and Charlie. So in order to check whether these model outputs are fair using the graph representation of the data, so we can measure this simple quantity. So what we do is that, so let's say Fi and Fj are the outputs on node I and node J, and Wij is the edge weight. So let's say where there's reason. So let's say for between Alice and Charlie, the edge weight is large. So if Fi is, let's say, Alice and Fj is Charlie, so because those predictions are different and the edge weight is big, so then this quantity, at least on that pair, will be large. So you want that quantity to be small for the algorithm to be individually fair using this graph representation. And so this quantity is also pretty well known in like a graph signal processing community. So it's also known as a graph Laplacian quadratic form. So it can be basically written in this nicer kind of matrix notation. So where L is just simply like a function of the graph adjacency, so W, and F is just a vector of our predictions on each node in the graph. So in order to do post-processing, we solve this optimization problem that consists of two terms. So of course, we are post-processing a model that we believe to be quite accurate. So the first term is we want to stay close to original predictions, so stay as close as possible. The second term basically says that our new predictions should minimize the graph Laplacian quadratic form that, as we discussed, measures individual fairness. So this is the objective function. So the cool part here is that actually it's a very simple optimization problem. So there is a closed form solution. So we can, let's say, if y hat is the original predictions that we have, and we have this graph that transforms into this Laplacian L. So it's very simple to compute the new predictions on this graph. So this post-processing algorithm, I'm not going to show the experiments with it in this talk, but it also works really well in the various types of settings. Okay, so our next step is training individually fair models. So here, let me first describe the intuition. So to train an individually fair model is kind of a variant of adversarial training. So the key idea here is you want to train a model that is accurate in the available data, and the data is similar in the fair metric. So, and I will show in a bit why is very related to adversarial training. So the rough kind of pipeline here is that we observe some data, then we audit the model that we have currently using DIF. So we find in the process of auditing, we find that auditor T, and we find similar data where algorithm performs differently. So now we just update the model parameters to minimize the prediction error because we want to be accurate, but also to make sure that the DIF is small, because remember, DIF tells us whether the model is individually fair or not. And then we kind of repeat it. So to make a connection to adversarial robustness, which I think is also kind of a topic that relates very highly to the trust in machine learning. And I know there is also other speakers in the seminars that talk about adversarial robustness. So in adversarial robustness, so oftentimes we are facing this problem that we have some input image and we can kind of corrupt it such that visually it looks exactly the same, but the prediction is changing. So the relation here is as follows. So we want to be fair with respect to all visually similar data. So we want to make sure that the outputs on two pairs of images, which are visually indistinguishable, are the same. So essentially what it means is that here in adversarial robustness case, we have a different fair metric, but otherwise our objective is the same. Okay, so let's kind of dig a bit deeper into how exactly we train those individually fair models. So we call our method sensitive set invariance, or abbreviated to sensate. So as I mentioned earlier, the objective function here is the loss function. So basically how accurate we are, plus the DIF times some regularization parameter raw. So as you can see, we use a DIF as a regularizer. So we just want to minimize the loss, but also make sure the DIF is small. So the DIF, unfortunately, as we wrote it, it kind of involved that auditor T and stuff. So it didn't seem like a simple thing to optimize. But here, borrowing some results from the distributional robust optimization for Wasserstein distance. So we can use the duality result and rewrite the DIF using its dual. So now it's actually, doesn't look so complicated anymore. So the DIF is equal to this, the dual variable lambda times epsilon, where epsilon was this threshold parameter, which basically says how much we can change the data points on average with respect to fair metric, plus the expected value of this quantity called R lambda. So what is R lambda? Well, it's basically, kind of the adversarial loss in a sense. Again, if you're familiar with adversarial robustness. So for each data point X, we want to find X prime such that it maximizes the difference in the outputs of the model H, but also we penalize the difference in the fair metric. So basically, we want to find something close in the fair metric dx such that the dy is big. So here, the dual is actually a lot simpler and computationally tractable. And more to that, we can write it as an expectation. So we can write the value of DIF as an expectation of this function f, where f, I mean, not the DIF, but the whole loss of sensate. So we can write it as a function f, where the f is just a loss on a data point plus this kind of value of R lambda on the specific data point. So because of that, we can actually use stochastic optimization, and we can train, it's like easily compatible with any deep learning models, and any other big models that you want to train. Also, I forgot to say, but if anybody has questions, please feel free to interrupt and ask them as I go. So I think it's, oh yeah, so I think Jing Fan asked to ask them in the chat, but yes, please ask any questions anytime. Okay, so let's go through some examples. So first, a simulated example to kind of visualize how the sensei operates. So we'll have this simulated data set where the points on the horizontal lines with basically identical y-axis values, we consider them similar. So it's of course like kind of a made up fair metric, but just to understand what the algorithm is doing. And so we simulated training data set with bias. So basically the probability of y given x is not constant on horizontal lines. So if you want to just simply minimize the loss, then we'll end up with something that is not fair with respect to this fair metric. And we will use the DIF regularizer. So basically we'll use our sensei algorithm to correct bias in the training data. So here is the training data. So it's in 2 dimensions. So here's the red dots are class 0, the blue triangles are class 1. So we trained like a small deep learning model here. So it learned this decision boundary. So it classifies pretty well, but clearly the decision is not constant along the horizontal lines. So in this case, it violates individual fairness with respect to this kind of fair metric. So now it's been increased parameter raw in the objective function. So it's a regularization strength of the DIF. So we get something that is more horizontal. So of course, now we are making more errors, but we are here improving the individual fairness. And because the way we created the data here, it wasn't possible to achieve perfect accuracy while simultaneously being individually fair. So we continue increasing the regularization strength, and kind of essentially as it becomes larger and larger, so we learn a decision boundary that is essentially horizontal. So that demonstrates that the algorithm kind of achieves its goals. So we can learn some like a predictor that is essentially invariant with respect to perturbations small in the fair metric. So again, here, because the fair metric says all points on horizontal lines are equivalent, so it means that whenever we evaluate DIF, we can take any point and move it anywhere on the horizontal line. The only way for DIF to be small if the decision function is constant, basically along the horizontal lines. So now we go back to our earlier examples. So we go back to the toxic comments classification. So we discussed it at the beginning of the talk. So we use this data from a toxic comment classification challenge from Kaggle. So it has 165,000 textual comments, and the task is to predict whether a comment is toxic or not. So how do we measure individual fairness? Well, again, as we discussed earlier in this talk, so we want to know whether the prediction is changing when we change some specific identity tokens. So the algorithm is not aware of this procedure for measuring individual fairness, but that's something that seems to be more intuitive from a user, from a human perspective. So we want to make sure that, let's say, predictions for my best friend is gay, my best friend is straight are the same. But in addition to gay and straight, as I mentioned, there are many different other identity tokens, and specifically there are 50 of them. That's what kind of the list was created by people who analyzed this data set before. So you want to make sure that the predictions on all variations should be the same to satisfy individual fairness. So essentially, for each test comment, we create 50 versions of it, and then we check whether the prediction is the same on all 50 or not. I think there is a question in the chat. So yeah, you mentioned the comparable pairs in the former part of the talk. What is the usage of those comparable pairs? So the comparable pairs are used as one way to learn a fair metric from data. So in this example, we didn't use that method. So we used a method that consists of comparable groups. So you remember how like one way to learn a fair metric was to say that there is a comparable groups of samples, and then we use PCA on them to extract these directions of major variation. So for example, in toxic comment classification, the comparable groups consist of these different versions of the input sentences with different identity tokens. So those represent comparable samples. Okay. So here, so the results. So again, we vary the regularization strength raw, and we kind of measure the balanced accuracy of sensei. The balanced is because the data set is quite imbalanced, and most of the comments are non-toxic, so balanced accuracy is a better measure. And we also measure prediction consistency. So as I mentioned, for each test sentence, we create 50 versions of it, and then we basically say, okay, if all the 50 predictions are the same, then the prediction is consistent, and then we measure on what percentage of test comments the predictions are consistent. So the regulation strength equal to 0 corresponds to basically a naive training, just empirical risk minimization. So we see that as we increase the regulation strength raw, so we improve prediction consistency very significantly from 65 to 80%. We also do suffer some loss in balanced accuracy, so basically about 2%. So here, like trying to achieve fairness comes at some cost of accuracy as well. So the other example that we discussed was occupation prediction. So here, the data set that also was collected by De Ortega and co-authors. So it's consists of 400,000 textual biography descriptions, and we want to predict one of the 28 occupations using those biographies. So here we measure individual fairness similarly. So we again measure prediction consistency, but the question here, does the prediction change when we kind of flip the names and gender pronouns in a biography? So again, we increase the regularization strengths. We see that here the original classifier was not too biased, but still using Sensei, we managed to improve prediction consistency. Also, what's interesting here is that the balanced accuracy did not really suffer. It even managed to improve by a very small amount when we increase the regularization strengths. So by the way, these tasks were performed, using so we fine-tune BERT and obtain the embeddings from BERT, and then kind of train the fully connected network on top of it. So that just to emphasize the scalability of the method that I earlier presented from a mathematical viewpoint when I talked about the opportunity to use stochastic optimization with Sensei. And so, as I mentioned, sometimes we kind of saw how enforcing fairness can sometimes hurt accuracy, sometimes it doesn't seem to hurt accuracy. So what is really going on here? So of course, if we enforce fairness, it's kind of enforcing additional constraints. So our in-distribution accuracy is likely to take a hit. Might be small, might be bigger. But what's interesting is that what if our data that we're going to test on is not in distribution? So what if the data that we will test on is, is not IID, but it's out of distribution data set. So for example, these problems are studied in domain adaptation. So data sets such as rotated MNIST is one of the benchmarks where we train on the regular digits, but then we test on digits that are rotated by some degree. So here, of course, a classifier that's trained to minimize the risk on the unrotated digits is not going to do so well on the rotated ones. And we can actually solve this problem using the sensei, as long as we have a fair metric, kind of quote unquote, that says that the image and all its rotated versions are the same or like very similar in terms of a fair metric. So here we can use a more creative ways to define fair metric to solve problems outside of the fairness domain and really kind of achieve some types of generalization. So again, for chairs, if you manage to come up with a fair metric that says that all these versions of chairs are the same, then we can train a classifier that will do well on all the kind of domains of office, home, and so forth. So this is also kind of part of our ongoing also work where we try to understand how the individual fairness can be used for domain adaptation and how domain adaptation techniques possibly can be used to train individually fair models. So this work also generated a bunch of references, so that's just for this to appear on the recording so people can follow up. So a lot of my ongoing work in this domain is kind of under this Tech for Justice initiative at IBM. So the project name is also Practical Individual Fairness. So after designing all these algorithms, I mean, especially in such areas, algorithmic fairness, you want to make sure that people get a chance to use them. And oftentimes the people who work in industry, data scientists, or maybe researchers in some other applied disciplines, they're not as intimately familiar with all the machine learning concepts. So it might be hard for them to just take a research code and adapt it, or to understand what exactly DIF is doing and so on. So that's why we kind of launched this like a collection of different initiatives that basically try to make individual fairness more accessible to practitioners and other applied researchers. So the key component of this is we are developing like a software that we call InFairness. So it's not yet available publicly online, but hopefully it should be there quite soon, like maybe before fall or even before summer. So it will be a package that one can install very simply, and then just import some functions and start training individually fair models, learning fair metrics, auditing, post-processing, and all the functionality that I've discussed. The other part of it, we also try to develop some interesting tools that allow visualization to compare fair and unfair models, for instance. So that just helps people to understand beyond the mathematical definition what is the difference between fair and unfair model. So here we kind of just see how when we perturb a data point from in a sense that it doesn't really it remains similar in the fair metric, so the decision doesn't change for a fair model and it does for a unfair model. So this is just an example, but we are trying to come up with more interesting visualizations as well. The next part of it, I'm very excited about it. It's kind of try to understand how data scientists perceive algorithmic fairness. So in algorithmic fairness communities, there is this notion of group fairness, there is notion of individual fairness. But again, data scientists might not be familiar with those. So the question is, well, what if I offer a data scientist two models and I tell them that they do, let's say, toxic comment classification, and they can start basically just probing different sentences. They can try to collect some aggregate statistics and so on. So it's interesting to see what people not familiar with this definitions of algorithmic fairness will come up to understand which models are, whether the models are fair or not, and also whether they will actually notice the difference between the fair and unfair model, as also a way for us to know whether our algorithms make a practical difference for the users. Finally, we also worked with the people in finance and Wells Fargo. So we wrote a review of individual fairness in finance applications. So those who are interested in finance application, please check out the paper. It's online already. So also we worked with the researchers in healthcare. So here we help them to evaluate different scores that are used by clinicians to evaluate atrial fibrillation risk. So in this case, it's actually the scores that the doctors, clinicians use in hospitals. So there are several options available. So for instance, the CHARGE-AF is one of the very common ones, but AHR-AF is more modern. It was developed by Massachusetts General Hospital, and kind of it's not yet as popular across the country. So here we evaluated, we kind of performed the individual fairness auditing and evaluated fairness of all these different scores, and we found that the HRAF indeed is actually more individually fair across a whole array of subgroups of people. So it's not not just overall, but also within basically every subgroup. by age, by race, by gender, and so on. Yeah, so hopefully, like HRF also actually appears to be good from the group fairness perspective, from the collaboration perspective. So it's another exciting application. And finally, we also published some blog posts and articles in media. So I think you can easily find them. So online, IBM research websites and other websites. And so with that, I would like to thank my collaborators. So a lot of people contributed to all this work, the research side of it and the applied side of it, University of Michigan, my colleagues at IBM, University of Constance, and Wells Fargo. And I would like to thank you for attending this talk. So if you'd like to find out more and kind of just stay updated on what's going on with the Python package or just other algorithmic developments, so please check my website, and I'm very happy to take any questions.
Hi, very appreciate Michael's great talk. Basically, I have questions. For example, when we identify some the metric for this is a sensitive metric or not, for example, the gender or something, is that a humanly crafted features or something? We have to put a lot of human efforts to locate those sensitive attributes.
You're talking about you're talking about learning the fair metric, right?
Yes.
Yeah, so we need to provide some input to the model. So it can be automated, but we need some labels, right? So it's basically, for example, we either need to have this information that this group of samples is comparable, right? Yeah. So that's one method that I described. The other method was saying some human needs to tell me like which pairs of inputs are comparable or incomparable. So it does, of course, require some effort, but so far we've been able, like whatever application we consider, we were able to figure it out relatively quickly just by kind of understanding what the potential fairness issues could be. And we also oftentimes find that the fair metrics we learn sometimes, I mean, not sometimes, but oftentimes actually, the resulting fair models, they end up also being robust or like fair with respect to some other unexpected questions. So as an example with names, so we were trying to make sure that the model treats names fairly, but then we found out it also treats like different countries fairly.
I see. There's some correlation.
Yeah, but to answer your question, there is some effort. I mean, it's just in supervised learning we need to provide labels. It's kind of like that. So
right. Yeah. Okay, that's perfectly also my concerns and questions. Hi audience. Do you have any questions? You can open your mic to see it, or you can also type it on the chat box. Yeah. Okay, I think that's maybe there are no further questions. Thanks again for Michael's great talk. Before you leave, I really essentially can hope in the future when the situation lifts, you could physically visit us in Tokyo. Yeah, when Nihonbashi office is in the right center of the Tokyo. It's a perfect place. We hope you can visit us in the near
That'd be
future.
great. I've never been in Japan or Tokyo so far, but it's definitely a place I would love to visit.
Yeah, great. Yeah, I think the situation will be relaxed very soon in the future. Okay.
Yeah, that's great. Okay, thanks a lot, Yuppang, and thanks everyone.
Thanks a lot for Michael's great talk. Great. Bye.
Bye.
Hi, Tianyu. Can you able to open your mic and share a screen?
Hi. Can you hear?
Hi, Tianyu. Yes, I can see you. Now I'm going to introduce you. Tian Yuppang is a final year PhD student in the computer science department at Tsinghua University, advised by Professor Jun Zhu. He received BS degree of mathematics and physics from Tsinghua University in 2017. His research interests includes machine learning, computer vision, especially on the trustworthy aspects. His research is supported by Microsoft Research Asia Fellowship and Baidu Scholarship. Hi, Tianyu, you can get started your talk. I can hear you.
Okay, thank you. Thank you for the introduction. Can you see my slides?
Yes, I can see your slides.
Okay, cool. Hi, everyone. Good morning. And I'm Tian Yuppang from Tsinghua University and CAI Live. today my topic is about the robustness and accuracy could be reconcilable. It's actually our recent work, and I will. The conclusion for Simple is that we claim that there should not be a trade-off between robustness and accuracy. So this is a joint work of my collaborators, including Minlin, Xiaoyang, Yinpeng Dong, and Professor Hang Su, Professor Junzhu, and Professor Shui Chengyan. Yeah. So here's the background. I will very shortly introduce the backgrounds. What we focus on is to solve the adversarial examples problem. And in the left column, in the left column is the clean examples, and after adding the adversarial perturbations, the adversarial examples in the right column will be can fool the model predictions. So here's the background of adversarial examples, and actually adversarial examples can also exist in physical worlds. For example, you can print the adversarial perturbations, and it can fool the practical systems. So adversarial examples not only exist in computer vision, it's actually a universal phenomenon in the machine learning community, including in language model and graph model, reinforcement learning, and audio, and also LiDAR, code generation, 3D point cloud, and recommender system. So actually, adversarial robustness is quite important, not only for the researcher in computer vision, but also almost all the researchers in the machine learning community. So that's the why we need to want to improve the robustness of our model. So, but there's a critical problem when we want to improve the model robustness. That is, there exists a trade-off between robustness and accuracy, either empirically or theoretically. So empirically, when we perform standard training, we can get a very high clean accuracy, but the robust accuracy is quite low or even zero. And when we use adversarial training to improve the model robustness, the robust accuracy will be significantly increased, but we will also sacrifice the clean accuracy. So you can see here's about a 30% drop on the clean accuracy. So here is some empirical observations. And theoretically, there are some works. They found that in some simple cases like hyperspheres or other simple distributions, this trade-off is inevitably exist. So this leads to a question that where the trade-off stems from. Yeah. So sorry, I will. Okay. So the first question is, what is an accurate model? So when we talk about the robustness between the trade-off between robustness and accuracy, we first need to figure out what is a robust model and what is an accurate model. So an accurate model refers to the one with low standard error. The standard error here is defined with respect to the KL divergence between the data distribution and the model distribution. So as you know, the KL divergence, when we minimize this function with respect to the model parameters, this is equals to the cross entropy loss we usually use. So it's easy to say that the optimal solution is the optimal model distribution is equals to the data distribution. So this is a definition of what is an accurate model. So what is a robust model? A robust model refers to the one with low robust error. So the most commonly used definition is proposed by Madras and others. So this definition, you can say there's a inner maximization problem with respect to the model distribution. So as you can see, generally the optimal solution is not equals to the data distribution. Yeah, so there will be, as said, the trade-off naturally comes, which means an optimally accurate model is not an optimally robust model. So which means there is a naturally trade-off, at least in their optimal solutions. So this leads to a paradox. That is, in the supervised learning framework, the data distribution is not an optimally robust model with respect to itself. This is weird because if the data distribution is not robust, then who is? So we even cannot explicitly well define the optimally robust model. So this is seems like quite counterintuitive or a paradox. So to figure out why this happens, we come back to where the Madras definition of robust arrow comes out. So actually, the Madras definition of robust arrow is a differentiable surrogate of the 0-1 robust arrow. In the 0-1 robust arrow, here, this is an indicator function. If the condition satisfies, it will return 1, otherwise it will return 0. So, and y theta is a hard label of model distribution. It's also, we call that the predicted label. And the yd is the hard label of data distribution, which we usually call the true label. So when the predict label equals to the true label, the indicator function will return 1. Will return 1, otherwise it will return 0. So this is a definition of 0-1 robust arrow. So actually, the 0-1 robust arrow is not the first beginning. It actually comes from a self-consistent, which we name it self-consistent 0-1 robust arrow. So you can see the difference is that in the self-consistent 0-1 robust arrow, we do not need to assume that the true label is the environment. We just make sure the model distribution stick to the data distribution everywhere in the site B. So there's several advantages of this definition because first we do not need we need no assumption on the data distribution. We do not need to assume that the true label is environment, and this makes us to able to allow for flexible size of B, which means the B do not need to be local. So the B can be quite large, and the points in B can have different labels. So this is a more general definition of 0-1 robust arrow. So after we adding the assumption that the true label is invariant in the local site B, we will lead to the what we commonly use the 0-1 robust arrow. So let's say let's have a summary. We first have the self-consistent 0-1 robust arrow, and when we add the assumption that the true label is invariant in Bx, we'll get the usually used 0-1 robust arrow. And when we make it as a differentiable surrogate, we will get the Madras definition of the robust arrow. So let's say there's two assumptions. The first assumption of the true label is invariant. This is reasonable because when we add a small perturbation, we will expect the label will not change. But when we make it to the differential surrogate, this assumption implicitly becomes that the model distribution is invariant. This is unreasonable because even if its hard label does not change, the soft distribution will change. So in this case, the Madras robust arrow assumes that the model distribution is invariant. This is an overcorrection towards smoothness, and that's why the trade-off happens. So based on this, we propose a self-consistent robust arrow, which abbreviated to SCORE. And this is quite simple. As you can see, we directly use a differentiable surrogate from the self-consistent 0-1 robust arrow. And in this differentiable case, we maximize the X with respect to both data distribution and model distribution. So they pointwisely stick to each other. And as you can see, in Madras robust arrow, they want local invariance, and in our case, in our score function, we want to equivariance. That's the difference. So in this case, the optimal solution of minimizing score is again self-consistent. Self-consistent means the optimal solution is again the data distribution. So in this case, the data distribution is both optimally accurate and also optimally robust model. So there's no trade-off between accuracy and robustness. Besides, this form also keeps the paradigm of robust optimization because there is still a inner maximization mechanism in this objective. So this is the two advantages of our objective. So here's a toy demo to show the self-consistency. So in the left part, this is the green line is the ground truth of the logistic regression. And here is the construct of the toy demo. And the green one is the model, is the data distribution, and the orange one is the model distribution. So in this case, we first sample 60,000 training pairs and mimics the expectation form of the loss function. So you can say in the first row, we minimize with respect to the measures loss, and after 5 pattern steps, the model converged, but the model distribution does not converge to the true data distribution. So which means it's not a self-consistent objective. And in comparison, when we're minimizing the score, after it converge, it can almost converge. Here's a little gap, but as an empirical gap. So it can convert to the true data distribution, which means it's a self-consistent objective. So in this case, because it's a toy demo, we can directly minimize with both. We can have a full access for both the data distribution and the model distribution. So we can take derivatives for both of them. And the second demo will show how the robust optimization works, because as you can see, for the standard arrow and for the score arrow, the optimal solution is both the data distribution. So they are both consistent, but in the standard arrow, there's not a robust optimization mechanism. So let's say what's the difference between them? So we use only 6 training pairs, which mimics the finite sample form in practice. So as you can see, although standard arrow has the same optimal solution as score, but it does not enjoy robust optimization in finite sample cases. So after we both run 5 steps and the model converge, our score objective can better have a smaller gap between the model distribution and the data distribution. So also you can say for the measure loss, the gap is quite large. Yeah, that's a toy demo show the effectiveness of our score objective. So as you say in previous demos, the score objective is quite promising, but the big challenge is in practice how to optimize score, because when we want to optimize score, we need to if we're directly applying the first order optimizers like SGD or ADAP, we need to calculate the gradient with respect to the this full KL divergence. So after we expand the gradient, we'll get 2 terms. The first term is the model gradient. It's the same as the when we used in previous work. So as you can see, this is just one step of when we craft adversarial examples in the previous work. But we will get an extra term, which depends on the data gradient. Here is the data gradient. So we cannot have access to the data gradient in practice. So one way is to use an actual model to try to learn the data gradient, like using score matching. But our initial experiments using score matching we found that the estimated score are of high variance, and it cannot easily apply into the into our learning process. So we leave this direction into our future work, maybe more advanced score matching like the new proposed one could be explored. So we do not use score-based method in this work. Instead, we substitute the KL divergence with any distance metric. As you can see, a distance metric is it satisfies two properties. The first one is symmetric, which means the distance metric is symmetric with respect to the two input variables. And the second property is the triangle inequality. So as you can say, it's like same as the when we learn in algebra. So a typical distance metrics include the LP distance. Yeah, so it's easy to verify that KL divergence does not satisfy symmetric or triangle inequality, because KL divergence first is not symmetric and it also does not satisfy the triangle inequality. So when we substitute the KL divergence in previous objectives with distance metric, you can say here originally here is KL divergence, but we substitute it with distance metric like here, and we get to new objective. And with these two objectives, we can get upper and lower bounds for score with using the R measures. So as you can see, here CD is a constant. It's independent of the model parameters. So it's an intrinsic property of the data distribution, which indicates the measured robust error of the data distribution itself. So let's first say the upper bound. The upper bound says that the R score is less than the R measured plus a constant. So when we want to minimize the R score, we can minimize R score D. We can minimize R measured D. So we do not need to estimate the data score anymore. We just minimize upper bound. This quite similar with the variational inference, where we will minimize elbow or evidence or lower evidence bound. So unless there's a lower bound, the lower bound indicates the overfitting phenomenon, because when we minimize the R measure D to minimize R measure D, at the first R score will be minimized. But when the R measure D is less than CD, the R score will become to increase again. So here's a toy demo to show this phenomenon. And the original, we choose the distance metric to be L2 distance. And the original line is corresponds to the R measure loss, and the blue one equals to corresponds to the R score loss. In the training, we minimize the R measure loss. So you can see in the older training process, R measure loss kept decreasing. But when we see the R score loss, it first decreased. At this point, overfitting begins, and it became to increase again. So at this point, what's this point? This point is the R measure equals to the C constant, which is the lower bound indicates. So we can also extend the theorem 1 to composite function of distance, because as you can see, here phi is a monotonically increasing convex function. For example, the square function, and phi d is the composite of phi and the distance metric. So examples of phi composite d include the squared arrow or the JS divergence, because the squared JS divergence is a distance metric. So in this case, we can also bound have an upper bound for the score function using a variance of the measured loss. So here's a empirical experiments show the effectiveness of the distance metrics and their variance. The first two first four rows is for distance metrics, L2, L1, and L infinity, and the squared, and the JS distance. And the last four rows are the squared variance. As you can see, the robustness, their variance has higher robustness compared to their distance counterpart, because in practice, this variance can better focus on hard examples. So it has empirically better performance. And the third theorem claims that when we use the distance metric instead of the KL divergence, we can say that the PDAT, which is the Madras method, and the trace, these two most popular adversarial training frameworks are equivalent, which is the equivalent means the trace objective can be bound by its upper bound is a constant times the R measure loss, and the lower bound is the R measure loss. So this is quite similar as the equivalence among LP norms. And it can induce the same topology of loss landscapes in parameter space, which means when we use the distance metric in the adversarial training objective, the trace and the PDAT could have quite similar performance. So in the previous part, we mainly talk about when we substitute the KL divergence with distance metrics, what will happen. And now we're back to KL divergence with new insights. So here's a bridge between the KL divergence and the distance metrics. That's the Pinsker's inequality. So in here, the Pinsker inequality says that the KL divergence is larger than the L1 distance, the squared L1 distance. So taking this into our previous theorems, we can derive a conclusion. In the right side, here our measure is the original KL-based robust error. You can see there's not a sub-index D here. So this is the original KL-based robust error that we usually minimize. And the left part is the R score with the L1 distance metric and the C constant with L1 distance metric. So this formula can explain overfitting and early stopping. Let's say that's why I can do this. So first, our measure is the objective that we minimize in previous work. And after we adding the condition for optimal solution, which means the R score equals to 0, we take this condition into the above inequality, and we will get that the R measure needs to be larger than the C squared over 2. So this indicates that we have to perform early stopping. We cannot directly minimize R measure directly to 0. That will cause overfitting. So in order to get an optimal solution, we need to early stop the R measure loss at this value. So when we say this deeper, we will say that when we have the optimal condition, there is the model distribution equals to the data distribution. So in this case, we take this condition into the R measure's loss, we will get that R measure need to be early stopped even earlier. That is, it need to early stop at the value of CKL. Here, CKL is actually the data distribution, the robust error of data distribution. So when the R measure has a smaller value than what data distribution should have, it causes overfitting. So here is a demo. Again, the original one is the R measure, but here is used the R measure used the KL divergence, and the blue one is the R score with the L1 distance metric. As you can see, when the measure's robust error is minimized to the CKL value, so overfitting will begin. So although the value of the R measure's loss still keep decreasing, the our score value will become increased. So it's overfitting happens. So on the other hand, our method can also explain semantic gradients. For example, for adversarial training, when we adversarially train models, the input gradient will have semantic patterns. So we show that under mute condition, the R score can be expanded with the to the R standard arrow plus gradient alignment term. This gradient alignment term is the alignment between the model gradient and the data gradient. So here is the data gradient, and here is the model gradient. So when we minimize the R metric, it's an upper bound of minimizing the R score value. So it's equals to minimizing the standard arrow besides an additional alignment term between these two gradients. So this is actually a gradient matching term to make sure the input gradient is semantic. So here is a demo way. We plot the input gradient of adversarially trained models. Here we plot 3 gradients, and as you can see, the conditional gradient has more semantic or perceptually aligned patterns compared to these 2 gradients, which is consistent or verify our theorem 4. Besides, we also can explain the semantic gradients for randomized smoothing. Here, randomized smoothing also usually use Gaussian augmented cross-entropy laws to train their classifiers. So here, the Gaussian augmented cross-entropy laws is defined as the PD sigma. PD sigma is a Gaussian augmented data distribution. And as you can see in previous work, they show that randomized smoothing can also lead to semantic input gradients. So to explain this phenomenon, our theorem 5 claims that this phenomenon could come from the Gaussian augmentation training precise, because when we can say that we can derive that the derivatives with respect to the Gaussian augmented cross entropy laws is equals to gradient alignment term again. So when we expand the Gaussian augmented cross entropy, it will equals to a cross entropy term without augmentation, and a gradient alignment term times to the constant sigma. So when we minimize these laws, it will also lead to a gradient alignment mechanism. So here's an empirical performance of our method. We first compare the performance of KR divergence and the square arrow on the small model like ResNet 18. So as you can see, our method, simply after we substitute the KR divergence with square arrow, we will have an improvement on both clean performance and auto attack performance. We also test the effective of the parameter beta in the trace method. As you can see, when we apply extra DDPM generated data, and the model is insensitive to different value of beta. So when we have beta equals to 3, 4, or 5, we'll have comparable auto attack performance, but the clean performance will have a significant improvement. So we also perform large scale experiments to compare with the state of the art. So as you can see, for example, on Specification, L infinity stretch model, we will keep comparable or even better auto attack accuracy, but we will improve about 2 or 3% clean accuracy on Specification. On Cipher 100, we also keep the comparable or even better auto attack accuracy, and the clean accuracy improvement is to can up to 3% to 5%. So it's quite significant. But as you can see, although we show that score can make sure there's no trade-off for the optimal solution, there is still empirical trade-off. So in our future world, the main challenge lies to propose more efficient learning processes. The first routine is to propose something beyond MLE or beyond the KL divergence. So we may need to resort to more advanced score matching methods, which based on the Fisher divergence to train the score objective. On the other hand, we may need extra data or robust architectures or more training tricks. So thank you. Here is the basically my talk, and the work I introduced today is this new published paper, new published paper on RCAP. And here are two other papers. The first one is the bag of tricks for adversarial training, which focus on empirical tricks, the effects of empirical tricks for adversarial training. It's a good guideline when you want to train an adversarial training model. So another one is focused on how to reject or detect adversarial examples. We show that there are we can construct two coupled rejection metrics that can probably tell what is correctly classified examples and what is a wrongly classified example. So if you want more information about our work, you can see my homepage, and there are codes public. Thank you.
Very appreciate Tianyi's great talk. I have a question for example, we know that when the epsilon is very, very small, regardless of LP norm, for example, L infinity or L2 norm, for example, epsilon is very, very small. Actually, it's not harm the robustness at all. It's also improve the generalization error, improve the clean error. Is it have this phenomenon have some linkage with your observation in this respect?
Yes, as you can say, in our bound. So when we minimize the KL-based robust error, so if we perform early stopping, the R score will also be minimized. Which means if we do not quite minimize or over minimize the R measure, it will benefit both the robustness and cleaning accuracy. Yes. So, but as you can say, for example, by Cihang Xie's work, they improve the cleaning accuracy on ImageNet by adversarial training. But they need to, for example, two batch normalization layers to make sure it works. Or otherwise, I need some tricks to make the cleaning accuracy to improve. Yeah, so in this work, our main contribution is to formally to show why we will we encounter overfitting, why we encounter semantic gradients, and whether in the optimal solution we can achieve the we can eliminate the trade-off between robustness and accuracy. Yeah. Because for example, in measures robust error, its optimal solution is not an accurate model. So there's an intrinsic trade-off between the robustness and accuracy. So no matter how well we optimize it. Yes. Yes, I got it. Because the previously there have some kind of phenomenon give us the feeling that as the epsilon increasing from 0 to slightly larger, they're kind of like a two-phase problem in terms of adversarial training. Yeah. So yeah, I'm wondering. Yeah, I get quite confused in this respect, but yeah. I'm really happy I can see your theoretical result explanation of this phenomenon of overfitting. It's a very inspiring and very great work. Thank you. Thank you.
Yeah. Is there any questions from our audience? Okay, if no, you can also email Tianyu if you have further question after reading his work. Then thanks again for Tianyu's great talk. We really appreciate it. Hey Tianyu, if when the situation lifted, I guess Japan will lift the situation very soon. We sincerely welcome you to visit Tokyo in our Nihonbashi office, if your time permits, of course. Yeah, in the future.
Yeah, thank you.
Great, thank you very much for giving us talk. Okay, this is the end of our today's seminar. Thanks again for our two speakers, Tianyu and Michael. Let's hopefully we can meet in the future. Bye-bye.
Bye-bye. Thank you.